Reflection of light. Is it really that important? Yep. Besides the mirror, we wouldn't be able to see each other if there was no reflection of light. Without reflection, you wouldn't be able to see anything, because any object that you look at, the light is reflected off that object and the rays then travel through into your eyes. In this unit, what we're going to do is I'll show you a neat way in which students can trace rays of light that have been reflected, and in this way uncover things like the laws of reflection of light. And then we'll also have a look at some fun things where these laws are applied. This is how I would do it. What I need is a plain mirror, a little bit of press stick, that teacher's friend, a block of wood that acts as a support to enable my mirror to stand upright. In front of it I place an object. The object is going to be a little pencil. Again, a little bit of press stick to hold the object upright in front of the mirror. And now I'm ready to trace the rays of light that are coming from external sources, bounce off that pencil, bounce off the mirror, and if I look at the image of the mirror, bounces into my eye. Conventionally we use pins, pin optics they call it. That's how the textbooks generally deal with it. But I find that confuses students, and what works out much better is, instead of using pins, use little kebab sticks. They represent your ray of light. So I have a look into the mirror, and there's my image. There's a ray of light coming from that image directly to my eye. So I use a little kebab stick to point directly at that image, because that's where the ray is coming along to enter my eye. So the ray comes along that kebab stick. I move to the other side, and the same thing applies. I put a stick along a straight line looking at that image. So now I've got where the rays have come from the mirror off that image. I then draw a line where the mirror is, remove it, and trace a line along the kebab sticks, because that is where the rays of light are coming from into your eye. Similarly on the other side. So the ray of light came that way, and it came into my eye, which is here. If I extend that ray, it appears to come from somewhere behind the mirror. And similarly here, where those 2 points meet is the position of the image. That's the object O. And of course then you go through your normal optics, draw angle directly vertical to that plane surface, use a protractor, and they'll see the angle of incidence equals the angle of reflection. They'll find that the distance in front of the mirror is the same as the distance between the image and the mirror on the opposite side. Students have got the angle of incidence equals angle of reflection, one of the laws of reflection of light. How can we apply it? Well, a lovely thing for them to build is a periscope. Very simple, not difficult to do. All you need is 2 little mirrors and a block of wood. I've cut grooves at 45 degrees into which you can slot those mirrors. So we put the one there so that it's upright, put the other one there, it's upright, and voila, you've got a periscope. If I look into this bottom mirror at an angle of 45 degrees to the mirror, it'll hit the top and show me what's coming out that one there. So I'm looking directly at the wall here. I can see rays that have come from there reflected down off that mirror and into my eye. Then here's a nice problem that you can pose for them. What happens if instead of looking in front of you, you place the top mirror so that you can look behind you? What do you think you'll see? Okay, and there I can see the picture quite clearly in my mirror. Well, what do we see? We saw the picture was upside down. And the obvious question then becomes, why? What's going on here? And so we can see the ray comes from the top of the tree, hits the top of this mirror, gets reflected down, out, comes out on the top. From the bottom of the tree, hits the mirror there, comes down to the bottom of the tree. So the tree is still upright when you look into it. But when we reverse the mirror, in other words, turn it through 90 degrees and trace the rays, we see the ray coming from the top of the tree, the red one comes down, is reflected, comes and it's on the bottom at this stage. And the one coming from the bottom of the tree goes along, gets reflected, and here we see it's now at the top. So the whole tree is inverted as it comes into the eye. Right, and here's a nice easy way of making a periscope that looks a little bit closer to the real thing. All you need is from your plumber's supply store, a couple of white pipes. One can fit just inside the other, and you'll need an adapter that fits neatly on that one, and then that fits into there, and I've got myself a periscope. The ray of light coming in the top gets reflected off that surface, down the tube, comes out into my eye. And so we're looking at that picture way up there, coming in there, down the tube, and into my eye. And there I can see the smiling teddy. And then one of the really cool things about this telescope is that as I'm looking forwards like that, if I then turn this around and get it to face backwards, wow, what do you think's happening? The whole world is starting to turn upside down until eventually I'm looking behind me and it's completely upside down, just according to the optics we've just explored. Right, finally, I've shown you some ideas here. If you have any ideas that you'd like to share or comments on what I've shown you, send your ideas in. I'll give you proper recognition and try and find a way of putting them up. Thanks.